Hey guys, this is going to be Chapter 15, Part 1. Alright, so Chapter 15 is all about chemical equilibrium. And so before we really get into it, we want to talk about chemical reactions and how they work, and then eventually what equilibrium is. But just so you know, dynamic equilibrium involves two opposing processes occurring at the same rate. And so the image that they show there is showing a highway with a bunch of cars traveling one direction and a highway with a bunch of cars traveling the other direction. And so they're trying to say that that's a type of equilibrium. And while I understand the analogy, I don't think it's a very good one. So something reaches a chemical equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. You can think of an equilibrium like in the classroom, where in my classroom, where two students would get up and walk out the front door at the same exact time as two students would walk in the back door. So the number of students in the classroom don't change, but the students that are taking up the seats changed. So the reaction is basically staying at a constant, but it's still moving in the forward direction and the reverse direction at the same time. So we look at the concepts of equilibrium, especially in chemical equilibrium, throughout this chapter, and reaction rates are related to chemical equilibrium because the chemical system is at equilibrium. The rate of the forward reaction equals the rate of the reverse reaction. So that's basically what I just said. All right, so the rate of a chemical reaction is the measure of how fast the reaction proceeds in a certain amount of time. So rate is always going to be divided by time, and chemical rate is usually measured as a change in the amount of reactant that we have divided by a change in time. And y'all don't have to calculate that or anything, but I do want you to know that in a reaction with a fast rate, that means the reactants turn into product or react to form product very, very quickly. And with a slow rate, reactants react to form product over a long period of time. So it takes sometimes thousands of years for a chemical process to occur. So rates can be controlled if we understand what causes a reaction to happen quicker. So we can make reactions happen faster if we know how they're controlled. All right, collision theory of chemical reactions. So chemical reactions, in order for a reaction to occur, two reactants have to actually hit each other, and they have to hit each other pretty hard. If the collision occurs with enough energy, then the reaction can go forward. If they don't, they just kind of bounce off each other. Since gas phase molecules have a wide distribution of velocities, collisions occur with a wide distribution of energies. So since some gas molecules move faster than others, reaction rates can vary depending on the reactant. And high energy collisions lead to products, low energy collisions do not. So that means that whenever the reactants hit each other with high energy, the reaction will move in the forward direction and make products. And when they don't, we're not going to have any product made. All right, collision theory of chemical reactions. So higher energy collisions are more likely to lead to products because most chemical reactions have an activation energy. So right here in the chart at the bottom left, this is the energy of activation. It's the amount of energy required to make the reaction occur. And so it's like a hill. Once you get up the hill, everything is fine. You have to get up that hill first. And so that's the barrier, and reactants have to hit each other with enough energy to overcome that hill. And so it doesn't matter if the reaction is like this, where this is an exothermic reaction, because it's lost heat, lost energy, because the reactants have high energy and the products have low energy, or if it's an endothermic reaction, right? Low energy reactants, high energy products. So that means it took energy in. So it's endothermic. It doesn't matter if it's exothermic or endothermic, you still have to overcome that barrier, the energy of activation. And so if molecules react with high energy collisions, then the factors that influence the rate of a reaction must be the same factors that affect the number of high energy collisions. So we need to look at that more closely. And so the two most important factors, and there are others that are important, but the two most important factors are the concentration of the reacting molecules and the temperature of the reaction mixture. So when we're looking at concentration, The rate of a chemical reaction generally increases with increasing concentration of the reactants. So if we increase the concentration of the reactants, that means there's more particles there. And if there are more particles there, they're going to hit each other more often. And if they hit each other more often, they'll hit each other with enough energy to overcome the energy of activation more often, meaning the reaction will actually go forward. So the more particles you have, and so here is less concentration, a little more concentration, a little more concentration, and the more particles you have, the bigger chance they have to hit each other. And then so temperature, if we increase the temperature of a reaction, then what's going to happen is the molecules are going to move more quickly, and they're going to have more energy. And if they have more energy, they can overcome the energy of activation faster. So more temperature means more energy, means faster reaction. And that's because they can overcome the energy of activation more quickly. And over here, higher concentration means more collisions. So you have a higher chance of an effective collision. All right, so the idea of dynamic chemical equilibrium is a reaction that can proceed in both the forward and the reverse directions is reversible. So in a chemical reaction, the condition in which the rate of the forward reaction equals the rate of the reverse reaction is called equilibrium. So there are some chemical reactions that are actually reversible. This condition is not static. Static means stopped. It's dynamic because the forward and reverse reactions are still occurring. So when we look at a chemical equilibrium reaction and it's at equilibrium, what that means is that it's going forward still and it's going in reverse. It's just doing it at the same rate so that you can't see a change here and you can't see a change here. So it looks like it's staying still, but it's really not. When dynamic equilibrium is reached, the concentrations of reactants and products no longer change. That doesn't mean that those reactions stopped, though. They're just not changing anymore. Because as the reaction goes in reverse, we make reactant, and as the reaction goes forward, we make product. And if it's happening at the same time, then nothing is disappearing anymore. The reactants and products are being depleted at the same rate at which they're being formed. All right, so when the concentrations of the reactants and products no longer change, equilibrium has been reached. And so if we look at the graph down here at the bottom, this is the reaction of hydrogen and iodine making 2HI. And the product is the dashed line, so that's HI. And the reactant is the H2 and the I2. So we start out with reactant and no product. And the reactant goes away because it's being used up to make product, and the product begins to be formed. Now around this area right here, we start to see that there's no change. The reactant didn't all go away though. There's still some left. It didn't go all the way to zero like you would expect. There's still some here. And so we've reached an equilibrium where the forward reaction and the reverse reaction rates are actually equal to each other. And so if we look at the picture on the right, we started out with 8 H2 and no HI, so no product. And after a certain amount of time, they put 15 minutes here, has passed, we make 4 HI and we've lost some reactant, which is what we would expect to happen. After another 15 minutes, we've doubled the amount of HI and we've lost some more reactant. And then if we wait another 15 minutes, there's been no change. So once we get to the point to where there is no change anymore, that's when we reached equilibrium. And that's basically equilibrium in a nutshell. Let me know if you have any questions.